retro toasters, laboratory furnaces, and aerogels. A rubber tree's lifespan for natural rubber production is limited to about 25 years. But making toys out of their wood gives unproductive trees a second life. This idea comes from Southeastern Asia, home to most of the rubber and latex production worldwide. This company based in Thailand manufactures toys, such as this series of animal-shaped racers, made of locally farmed rubber wood. They buy old trees that have exceeded their productive life. A worker feeds lumber through a wood rounding machine. The machine drives the log through a mill and turns it into a rod. The worker places the rod on a tray alongside other pieces ready for cutting. A cutting machine automatically matches the length of the rods, while a round saw cuts out blanks, which accumulate in a crate. A router removes the sharp edges on the blanks. Stacked in a feeder tube, the blanks drop down one by one on the router table. An automated feeding mechanism pushes each blank against the router head. The router blade bites into the blank and trims off the edge, leaving the pieces ready for sanding. At another station, a lathe turns spherical shapes out of the wood. Several blades move in sequence to form the piece. When a new length of wood comes through, the front blade moves in. Once it backs away, another set of blades shapes the piece laterally before a cutter blade separates it from the rod. A worker now pours a non-toxic water-based paint over the sanded blanks. He transfers the batch into a tumbling machine. The tumbling process will even out the color and drain the extra paint to accelerate drying. The worker closes and secures the lid of the tumbler before he starts the machine. The facility can simultaneously process 40 batches of painted parts in 30 minutes. The painted parts now go to a pad printer. An automated arm feeds the painted parts to the printer, which stamps each piece with a non-toxic paint. A worker uses a table saw to groove another set of painted parts. The custom-made jig ensures that the cut is straight and even, and that the blade makes only a narrow and shallow groove in the wood. The worker places the grooved part on a jig and bores a hole into the piece with a drill. The machine piece goes to another pad printer. The pad picks up paint from a tray and transfers it to the wood. This process, called tampography, allows the printer to reproduce a design on an irregular surface, such as this wood piece. The printed parts dry at room temperature. As a last pad printer paints 2 dots on the wood, the face of the animal racer slowly takes shape. This red-colored powder is processed rubber wood sawdust, entirely recycled from the machining operations. A worker fills molds with the reprocessed sawdust and prepares them for casting. The machine compresses the sawdust in a die and turns it into a solid and compact material called plan wood. A worker starts assembling the plan wood pieces to form the body of the racers. She applies a thin coat of non-toxic formaldehyde-free glue and presses 2 corresponding plan wood pieces together. She removes the excess glue with her finger before she hammers a dowel into the assembled plan wood body. To finish the head of the racer, she inserts a felt piece into the groove machined on top and presses the head into the racer's body using a pneumatic press. The worker then drives the axles through holes in the plan wood assembly. She takes painted and pad-printed wheels and applies a drop of fast-hardening glue inside each wheel hub. She then hammers the wheels into the axles, takes the assembled toy to a customized machine designed to press the wheels firmly into the axles. This finished chicken racer is one of a wide variety of rubber wood toys manufactured with environment-friendly processes and materials. Whether your preferred shade is light, medium, or dark, owning a reliable electric toaster that evenly heats and browns both sides of your bread just the way you like it is one of life's small pleasures. And if that toaster adds some style to your kitchen, all the better. Making retro-style toasters is this British company's bread and butter. While some of its models are new designs in a vintage style, this one is authentically retro, in continuous production since the 1960s. The manufacturing equipment, however, is modern. A computer-guided laser cutter cuts out many components from sheet steel coated with zinc for corrosion resistance. They stamp the company logo and then use the same press to begin forming a rectangular box. They bend 3 sides on this press, then bend the 4th on a machine called a box folder. They rivet the body closed, then spray on a thick layer of paint powder known as powder coat. Then they run the body through a tunnel oven for 10 minutes to bake the finish. The computer-guided laser cutter also cuts out several toaster tops from a sheet of stainless steel. This model is a 4-slice toaster, so the machine cuts 4 slots per top. To make the manual bread ejector that pops up the hot toast, they weld steel strips to a round steel bar. Moving the toaster's ejector knob lifts this bar, raising the top of the toast out of the slot. They bend the strips, creating a cradle to stabilize the bread so that it doesn't wobble and get caught while moving up and down within the slot. This machine makes the toaster's guard wires out of copper-coated steel. The guard wires are barriers that prevent the bread from touching the toaster's heating elements. The machine first welds cut horizontal wires to 4 continuous vertical ones. Then a blade chops the vertical wires every 12 inches, producing 2 side-by-side guard wires. Workers cut them apart on a guillotine. Then, with a hand press, fold over the top of each one. This prevents the bread from catching on the top of the guard wires. Now they take the toasting compartment and insert the 8 guard wires, 1 for each side of the 4 bread slots. Then they install the bread ejector. Next, the heating elements. Being a high-end toaster, the elements are sheets of pure mica, a mineral that's heat-resistant up to 1800 degrees Fahrenheit. They connect them with electrically conductive copper links. They mount the switch that selects the number of bread slices to toast. Then they install a red neon light that illuminates when you start the toaster and turns off when the toast time has elapsed. The timer switch has a bell that sounds when the toast time is up, at which point the switch cuts the current to the elements. They attach the dials for the slice selector and timer switches and connect their wires to the main power cord. Then they place the toaster compartment into the body and screw on the toaster's stainless steel top, the protective film now removed. They flip the toaster upside down and wire up the elements. They install the ejector knob, positioning its spring against the bread ejector. When the bell rings, indicating your toast is ready, you move the knob to raise and retrieve your slices. A technician tests the toaster thoroughly, ensuring that all the elements heat to the correct temperature, that only the selected slots heat up, that the timer is accurate, and that the bell rings when the selected time elapses. They install the removable crumb tray, then close up the bottom of the toaster with a ventilated base plate. Nylon feet elevate the toaster for ventilation and to prevent the screws attaching the base from scratching your kitchen counter. The style may be retro, but this 1960s design toaster was ahead of its time with its energy-saving slice selector feature that stops the toaster's empty slots from heating up unnecessarily. Laboratory furnaces are small but powerful appliances. They can reach temperatures of 3,000 degrees Fahrenheit or more. These incredible furnaces are often used to test the quality of things like fuel oil, greases, coal, and to confirm the strength of structural materials. Exposed to the red-hot intensity of a laboratory furnace, this piece of steel should endure and even be strengthened by the exposure. It's the ultimate test of the steel's integrity. Making a laboratory furnace starts with this laser cutter. It carves out steel panels for the lower cabinet. A press brake folds the panels with precision to make three-sided pieces of cabinetry. A worker stacks them up. The next worker applies a powder coat to the metal parts using a compressed air sprayer. When baked on, the powder forms a tough thermoplastic skin. At the next station, a worker tucks the end of an iron alloy wire into a lathe. As the lathe spins, it winds the wire around a mandrel, producing a tight coil. This coiled wire will serve as one of the furnace's two heating elements. After stretching the coil to widen the gaps and bending it to create parallel rows, the technician attaches electrical clips. He flips a switch and electricity surges through the coil. This relieves stresses in the metal caused by the winding and bending. He now inserts two coils into the ridges of a mold. He transfers it to a vat filled with a ceramic fiber mixture. A powerful vacuum pump pulls the mixture into the mold, filling all the crevices. The vacuum then draws out the moisture. The coils are now embedded in a ceramic cake. This cake bakes in an oven overnight and solidifies, encasing and insulating the heating coils. A worker cuts the solid ceramic fiber block in two, creating two separate heating modules. He trims them so they fit neatly in the furnace chamber. A computerized router cuts out other insulation pieces to fit the rest of the furnace chamber. This ceramic brick is a threshold insulator. This piece is a surround for the furnace door. A team now puts all the ceramic fiber pieces together in a metal framework. The heating element blocks form the sides of the furnace chamber. They thread the wires from the coils through the back panel. They insert the side and back panels in the framework. They assemble the other ceramic fiber parts to form an insulated chamber. They screw the framework tight, and this nestles the ceramic fiber walls more closely together. They tuck the threshold insulator into place, completing the laboratory furnace's heated chamber. A technician now places the furnace's electric heating control panel in the lower cabinet. He fastens it to the metal cabinet with screws. He wires the temperature control board to a touch screen and connects the power supply for the touch screen. He installs a stainless steel shelf on top towards the front. He screws the front panel that houses the touch screen to the cabinet. He adds the top panel that the furnace chamber will sit on. He assembles the metal surround for the furnace chamber to the control cabinet, then slides the furnace chamber into place. Moving to the open back, he wires the heating elements for power and inserts a temperature sensor into a hole in the center of the chamber. He assembles a connector block, which will relay the sensor signal to the controller. He encloses the back with another metal panel. The next technician hinges the door to the metal surround. The door is a metal structure that's filled with many layers of ceramic fiber insulation. He lowers and raises the door to confirm that it operates smoothly. This metal cover is the finishing touch. He snaps it onto the door and secures it with screws. The laboratory furnace's thick insulated chamber is ready to contain the extreme heat and maintain it. And these torrid conditions are ideal for quality control testing. Gels are the lightest solid materials on Earth. They have nano-sized pores that make it difficult for cold or hot air to penetrate. Used to insulate the electronics of the Mars rovers and to capture comet dust, aerogels are among the most fascinating materials. Aerogels in shaped forms look almost like holograms, yet they feel like hard foam. It's why they are often called frozen smoke or solid smoke. Making them starts with 4 ingredients: a chemical called TMOS, methanol, concentrated ammonia, and water. The technician adds measured amounts of TMOS and methanol to a beaker that has a magnetic stir bead at the bottom. He transfers the beaker to a device that generates a rotating magnetic field. This causes the bead in the bottle to evenly mix the ingredients. He pours the mixture into a larger beaker and adds specific amounts of water, additional methanol, and ammonia hydroxide. As the ingredients are blended, a chemical reaction occurs. The TMOS and water react to form silica. The chemical reaction will also cause the mixture to become a gel. But before that happens, he quickly prepares the molds. He pours pure methanol over a plastic grid and arranges rectangular molds over the grid. He injects precise amounts of the silica gel mix into the molds and leaves them to gel. During this process, the methanol under the grid evaporates, preventing excessive drying of the gels. The mixture coagulates in just minutes, but it takes about a day for the gels to fully strengthen. He then soaks the silica gels in methanol baths repeatedly over a period of several days. The methanol seeps in the gel's pores to flush out impurities. The gel pores are so minuscule they can't be seen with the naked eye. The technician decants the used methanol into a container. He'll send it to a recycler to remove impurities, and this will allow it to be used again in the aerogel production process. After several days of soaking in methanol, the silica gels are purified. They're ready for a process known as supercritical drying. It's a process that will convert these silica gels into aerogels. A technician places the gels in a pressure vessel. He locks the heavy steel lid with 12 large bolts and nuts, so it will hold tight against a pressure that's 100 times greater than that of the normal atmosphere. He connects the hose that delivers liquid carbon dioxide to the vessel. The liquid carbon dioxide replaces the methanol in the gel's pores. They then heat and pressurize the gels until the carbon dioxide in them becomes supercritical. It's semi-liquid, semi-gas. The supercritical carbon dioxide diffuses out without collapsing the gel's solid skeletons. This transforms the silica gels into transparent solids that are mostly air. To demonstrate the insulating properties of the nano-sized pores, they aim a blowtorch under an aerogel with a peanut butter cup on the top. It doesn't melt. A technician then places the aerogel on a scale to confirm its incredible low density. This aerogel weighs less than a nickel. Next, using a scupula, which is a tool with a V-shaped dent, she breaks an aerogel into little pieces. She inserts the bits into a glass tube with a bulb at the base. She transfers the tube to a machine that measures how much nitrogen gas the aerogel bits take up at different pressures to determine the size of the pores and the surface area. Aerogels can have other magical properties. To demonstrate, she rubs specially treated aerogel particles on her hands. She then plunges her hands into water. The aerogel particles act like waterproof gloves and repel the water. This water resistance makes aerogels useful for a variety of applications. They can be added to paint or other things to make them waterproof and add insulating properties. Scientists continue to explore the potential of aerogels. A gossamer synthetic material that weighs almost nothing, there's a lot more to them than it may seem.